without further ado, I can start introducing the first speaker. So let me stop sharing. So you can start sharing your screen, Chao-Yang Lu, while I introduce you. And Professor Chao-Yang Lu, he obtained his bachelor degree from the University of Science and Technology of China in 2004, and his PhD in the Cavendish Laboratory at the University of Cambridge. His research interests span from quantum computation, solid-state quantum photonics, multipartite entanglement, quantum teleportation, superconducting circuits, and atomic arrays. And he's one of the leaders of the quantum advantage experiment with photons that I believe he will talk about that right now. So thank you very much. And feel free to share your screen now. Sorry for these problems.
Thank you. All right, so it's fairly late night in China. It's almost midnight. So everyone, good morning, good afternoon, and good evening, depends on your time zone. So first off, I would like to thank for the organizers for giving me this nice opportunity to present our recent work on quantum light source and quantum computational advantage. So I always begin by citing the Google research roadmap that, we very much agree that we should emphasize both on the qubit quality and quantity. And despite all the hypes, obviously we all agree that the fault-tolerant quantum computer is still a distant goal. So a realistic roadmap for quantum computing would be one way is, as we put in the Chinese national initiative, laying eggs along the way. So the near term was to demonstrate quantum computing advantage, which means to build a quantum device that can solve a well-defined problem, not necessarily useful, but should be overwhelmingly faster than any classical computers. So showing the quantum speed up in actual experiments will not only enhance our confidence to the next two steps, but also, it is fundamentally important. So the idea of quantum computational speed up, since proposed by Richard Feynman 40 years ago, exactly, it's a widely believed but unproven conjecture. So as shown in this review article, just like using the Bell experiments to refute Einstein's local hidden variable model and establish the quantum entanglement as a valuable resource for with stronger than classical correlations. So the quantum advantage experiment will refute the old extended Church Turing Thesis and prove the potential of fast than classical computation using quantum mechanics. So Google and USSB have focused on random circular sampling using superconducting circuits. Sergey's talk later will discuss their fantastic work in detail. They were able to build an extremely high quality 53 qubit Sycamore system along with very nice theory, and with that they were able to obtain 1 million sample, which they estimate would take 10,000 years for a supercomputer. So I would like to steal one slide from Vazirani. He also pointed out that quantum supremacy is not a single shot achievement, but will be like the Bell experiments. It would be nice to be refined over time to eliminate possible loopholes, because the classical computer scientists are very, very clever, and they will come up with better and better algorithms. So the quantum algorithm we are interested in is boson sampling using photons. Here, it's just a simplified model for linear optical quantum computing. It's a much easier model. So we have an array of quantum light source sent into a large interferometer, and as output distribution are sampled. So the classical method to do the sampling is to calculate the corresponding submatrix permanent. And the permanent is notoriously hard to compute and is believed in the Shao-P hard class. So in 2013, Scott Allison, who just won the ACM prize in computing last month. Congratulations to him. And his student Agipov proved that even approximate or noisy classical simulation would imply a collapse of the polynomial hierarchy. So it's such a beautiful theory that I have been inspired and hope to realize, as I said in the interview with Nature 5 years ago. So when we actually started to seriously consider how to realize a larger scale boson sampling, we about 7 years ago, we collect all the best figures of merit in the best source, best circuit, and the best detector. And we put everything together, if they can put together compatibly. Even that, we would estimate, we estimate that if we will perform a 50 photon experiment, the counter rate will be 10 to the power of minus 150 hertz. So this is obviously an extremely small number, and the probability is about, you need to win millions of dollar lottery 20 times in a row. So it's extremely small probability. So why is so low? What are the problems? The main problem is the lack of a reliable quantum light source. Ideally, a single photon source should simultaneously fulfill the checklist. The generation, collection, and the detection should have high efficiency. The emission should have near zero multi-photon probability, and the photons should be identical to each other in all degree freedoms. So they should be indistinguishable fundamental particles, as we in the quantum mechanical textbook. So what are the existing quantum light source? One, the most used workhorse for multi-photon experiments is SPDC. And it is well known that SPDC has intrinsic problem that as emission is probabilistic and can have multi-photon contamination. It is, however, less well known that actually after 2 decades of development, the SPDC was still not optimal, with unsolved problems in the collection efficiency and also in the efficiency quality trade-off. So for example, the entangled photons were usually collected from the intersections of the two down-converted rings, which are not in a good Gaussian shape, so they cannot be coupled into single modifiable with 100% efficiency. So in 2016, we engineered SPDC so that the two rings are converged into two separate circular beams, which is more favorable for single photon collection. And another example is unwanted spectral correlation, which you can see from the tilted spectral correlation, which means there's energy correlation. So the phase matching condition should be adjusted so that in 2018, we create SPD source, which makes the correlation circular. So we do not need any narrowband filtering to make the independent photons indistinguishable. So this is one source. Another source, currently the best single photon source is quantum dot, which we also call artificial atoms. For quantum dot, actually, it also suffers from similar problems. I think it's fairly common that we have the problem of quality and quantity problems. So for the quality problem, so the indistinguishability of the single photons from quantum dot strongly rely on the method of optical excitation. So previously, the predominantly used method is non-resonant excitation, which causes uncontrolled time jitter and electric field fluctuation, which fundamentally limit the photon indistinguishability below 60%. So to solve this problem, we developed pulsed resonant excitation, which coherently drive the two-level system, so avoided the time jitter. It's directly drive. So, and as you can see, there's a very nice Rabi oscillation, and the pi pulse laser power is only a few nanowatts, which is 4 order magnitude lower than before. So greatly reduce electric field fluctuation. And with that, the photon indistinguishability was increased to 99.5%. The next problem is photon collection. And to make the emission predominantly directional, we couple the emitter in a micropillar. And here the emitter lifetime is shortened to about 80 picosecond on resonance from 700 picosecond off resonance. And the extraction efficiency is increased from about 1% at bulk structure to about 66%. The number is keeps increasing, and I will show later. So we have new numbers. So the resonant excitation and is a microcavity is promising, but it is not the end of the story. So the use of resonant excitation, which makes the photon quality almost perfect, actually came with a price, because now the laser is exactly the same wavelength. So we have to use polarization filtering to suppress the laser leakage, which, however, all at the same time, cause efficiency loss of about at least 50%. So we design new protocols that solve the two problems simultaneously. So here we use asymmetric cavity, not a symmetrical one, asymmetric cavity, which split the cavity mode into two non-degenerate and linearly polarized mode, H and V. So we put the emitter on resonance with one of the cavity mode, say horizontal. So the Poisson enhancement is polarization selective. Most of the generated single photons will be funneled into this H polarization. And second, we design orthogonal excitation collection protocol. That is, we will excite with V and collect with H. And the V cavity is separated, but not separated too far away, so we can still excite this system. So this is actual elliptical micropillar we fabricated, and then we generate polarized single photons with every figure of merit, every checklist simultaneously fulfilled. So this gives us, in principle, a perfect single photon source. And based on the single photon source from quantum dot, we scale up to from the previous mostly 3-photon experiments to 20-photon experiments and 60 mode interferometer in 2019. And the output space dimension is 10 to the power of 14. At that experiment, the single photon count is about 16 million per second, which was the highest. But currently, we have more than 45 million single photons count per second, and we can easily scale up to more than 30 photons. So why we are interested in 20 to 30? Because originally, from the old estimations, we thought 20 to 30 should be sufficient to show quantum speed up. But in 2017, a classical algorithm improvement from Bristol raised the bar to 50 photons. So how to go beyond 50 photons? So very interestingly, there's a scheme called Gaussian boson sampling, which came as a rescue. So important feature is that when most of the previous multi-photon experiments were afraid of the multi-pair emission and only exploit the tip of iceberg of the SPDC, but the Gaussian boson sampling can overcome this limitation. So I will first briefly explain the working principle of Gaussian boson sampling. But before that, let me go look at the original boson sampling again. So in the origin Arkhipov boson sampling or Fock state boson sampling, the complexity lies in the superposition of many possible paths that can lead to a certain multi-photon coincidence. So for example, if we start from 1, 2, 3, 4 as input and 1, 3, 4, 7 as output, there are more than 20,000 possible paths that will coherently adding up together. Now, in Gaussian boson sampling, instead of using single photons as input, which was expensive experimentally, as I show, after more than 2 decades, we still, we are still developing better source. So in Gaussian boson sampling, GBS use squeezed vacuum as input, which is much easier to prepare. So what is a squeezed vacuum? It is a coherent superposition of different even photon number states with a fixed phase relation from 0 photon, 2 photon, 4 photon, 6 photons, and so on. So what is new here in terms of the computational problem? So what does the Gaussian boson sampling brings in on top of the spatial superpositions as in the Arlington-Akipov boson sampling is that there's also different input photon number combinations. So for example, if we still detect the 4 photon in the output, but it came from a combination of different photon number input, for example, 4 0 0 0, 2 2 0 0, 2 0 2 0, and so on. And the output distribution is related to a matrix function called Hafnian, which is also related to permanent, and is believed to be also in the sharp P hard problem. So now from the idea to experimental implementation. So in the first experiment, we sent 50 single mode squeeze state into a 100 times 100 interferometer. And in the second work, our interferometer is increased to 144 mode. And so there are a number of challenges which I will discuss in detail later. So for the source, we use a custom designed pulse laser with a repetition rate of 200 kilohertz instead of the routinely used 80 megahertz because we need higher peak power. And we use a deformable mirror to compensate the high order dispersion so that the output spectrum is transform limited, as you can see from the intensity and the phase data. And the laser is split into 25 modes and focus on 25 ppkdp crystals. The output is frequency uncorrelated, as you can see from the spectrum. So one problem, obviously, the laser power is always limited, no matter how high a power you are. So how can we scale up from this scheme? In our recent experiment, Jiuzhang 2.0, we borrow idea from laser and we design stimulated PDC, which allow us to make more efficient use of the laser power. So for example, in this case, if we double pass, then we will have 4 times brighter squeeze light, or we can just use a quarter of the laser power before. And we generally squeeze laser with higher brightness and also higher purity and efficiency simultaneously, as you can see from these two plots. So as I mentioned, the Gaussian boson sampling is can take advantage of the photon number superposition, but this also came with a price that we have to phase control all from the photon generation to the interferometer, which is not like the original boson sampling, where there's no phase relation in the source. So with active and passive locking, we finally managed to stabilize within 25 nanometer overall drift. And in our recent experiment, we have improved it from 25 to 15 nanometers. These are the two the metrics we generated, the amplitude and the phase, so it looks pretty random. So the whole setup looks like this, from the custom-made laser system to quantum light source. Each are collected into optical fiber. So optical fiber is wind along piezo for phase locking. And this is our second generation using the stimulated SPDC and it's a 144 mode photonic interferometer, which looks like this now. So now we analyze our experiment result. We can divide our results into 3 different regions, which we call easy region, sparse region, and the intractable region. So the easy region is at a small scale where we can get the full output distribution, as in the most previous proof of principle experiments. So after building the setup, we need to calibrate the system. And for the calibration, we choose the easy region. We only let in 3 pairs of squeeze state, and we get the full distribution of the output. And for the 23 different combinations, because we have the full distribution, so we can estimate the fidelity of the experiment to the theory, which is on average 99%. So give us confidence that the machine is running properly. So when the photon click is more than 4, then there's only a small fraction of the output can get 1 event, while most output will have 0 event, which is called the sparse region. And finally, when the output click is more than 40, then calculation of 1 metric function will become classically too difficult. So if we let in all the 25 input, we get output photon distribution at a different laser power. At the highest laser power, we get maximum photon click of 113. And we also measure the low power data, where the maximum click is about 20. So because we would like to welcome everyone to play with our data with their laptop, because this region is, you have to run a supercomputer, which is expensive. But this region, 0 to 20 photons, you can just use your laptop to play with the data. And the size of the output hyperspace grows exponentially. And now we are up to 10 to the power of 43. So at such a huge hyperspace, there's a significant and open challenge in the verification. Okay, 5 minutes. In the verification of boson sampling results. It's not like the Shor's algorithm, where the solution can be efficiently verified. So for the GPS, due to the nature of sharp P problem, which means both directions are difficult. So by definition, a full certification of the outcome is generally believed to be intractable for classical computation. So what the boson sampling community can do at the moment? So the traditional solution is to provide evidence to the quantum mechanical nature of the GPS device and rule out all possible hypotheses that is plausibly to occur in the experiment. So one is to input with thermal state, which would result from have large photon loss. Another one is from indistinguishable photons, which can cause by mode mismatch. And we also we hope to exclude all possible other hypotheses, such as uniform samples, thermal squeeze thermal states. So first we look at the whole distribution from the left figure. You can see there's strong deviation in the line shapes and the peak positions between our data and all the various kinds of the hypotheses we can think of. You can see our data is in very good agreement with theoretical prediction, but different from all the other hypotheses. And next, we look into a subsystem with fewer output bosonic mode. So say they are in total 144, but first we look at the first 80s and increase to 90s and 100. So we use the standard Boson test. We define Boson, the delta H, to measure the strength of validation. If delta H is negative, it means the experimental samples are more likely to be generated by GPS machine rather than the mockup. So we validate all possible hypotheses we can think of: thermal state, squeeze thermal state, coherent, distinguishable, uniform samples. And importantly, we can not only rule out all these mockups in the subsystem, but also we can see the strength of validation becomes stronger when the subsystem increases. So it's reasonable to infer that the validation will succeed in the supremacy regime, although we cannot compute directly. One thing we have to acknowledge is that the theoretical modeling of boson sampling is not as complete and advanced as random circuit sampling. So as we wrote in the paper, we hope our experiment will inspire new theoretical efforts to calculate and verify large-scale GPS, and we welcome challenge from a broad community. And you can download the data from this website. And I come to the end of my talk. One last point I would like to mention is that a GPS machine is partially programmable. So the phase and the amplitude can be tuned. And recently we tried 30 different phases, and they are statistically different. You can tell the difference. And what's next, we hope to make the interferometer fully tunable. And we look for, there are a number of existing theoretical papers, but we would like to identify if those have really any genuine quantum advantage. And I would like to wrap up by stealing a well-known slide from John Pressgill on the frontiers of physics. I don't have time to go through, and where I would like to acknowledge people. So Jiang Wei Pan and I conceived the project together, and this is our team. Compared to what Sergio just showed, the Google team, our team is much smaller, but they are the real heroes. These brilliant minds, the real heroes are my students and the postdocs who did the hard part of the work, and it has been great fun to work with these brilliant minds. Okay, thank you very much for your attention.
Okay, so if there are any questions, please type in the chat. I will start. We have time for a couple of questions at least. So the first thing that I wonder is, what was, you have to solve many experimental problems with the photonic sources and detection, etc., to realize this experiment. And what was the most challenging one, the one that took you more time to solve of all the problems that you listed? Sorry, you're muted. No.
Yeah. So yeah, it's a good question. So over the years, I think we put our most effort on the quantum light source, because I think the source is the most crucial one. So we gradually realize that the quality, the photon quality is we need to improve the quality. Then we improve the quantities, efficiency. Then we realize there's always a trade-off, and we think of different ways to make them compatible. And yeah, I think that is the most challenging one, but also I think others are also very significant. For example, the phase locking from the source to the interferometer, they are 22 meters long, and they are 50 paths. We need to make each one to be controlled within like about 10 nanometers, and we spent more than a year on how to learn how to make this system stable.
Okay, thank you.
Hi, Chao-Yang. It's so great to have you here visiting Toronto virtually. Hopefully one day we'll see you in person too. Just a quick question. So in terms of what's next, practical applications, we a few years ago proposed to use Boson sampler to simulate molecules, for example, as a potential application of this type of technology. Have you guys considered trying to simulate some molecular baryonic spectra, or by any other so quote unquote practical application beyond this? Like what's next, basically?
Yes. So yes. So what you mentioned is our highly interested area of interest. So our general feeling is that, so quantum computers in general will first solve the quantum related problems rather than the classically related problems. And the quantum chemistry, as you propose, the spectrum, and also recently I think there's a protocol called single electron transport assisted by the GPS are quite promising. But the other problems, we feel like the quantum machine learning and the other problems are more unlikely to really show the quantum advantage. I think the real quantum advantage will first appear, we make the quantum computers to first solve quantum problems rather than classical problems. That's our strong feeling. And yes, and your very early protocol on 2015 on the molecule spectrum are, one of our most interested areas.
Okay, so one more question from Nicolas Quesada. How do you verify that the joint spectral amplitudes of your squeezed states in the high gain are identical? For the first experiment, you have brightness between 4 and 10 in mean photon number, where there is no obvious guarantee the Schmidt modes match. It's in the chat.
So we have, so in our quantum dot lab, we have 1550 wavelength region spectrometer. So we set each, a very narrow window, and we scan the entangled photons. So that's our experimentally measured data. Actually, our first measurement was in 2018, where we published in the 12-photon entanglement paper.
Okay, thank you very much. We have to pass to the next speaker, and there are a couple of questions more in the chat, so feel free to answer these questions there. And thanks again, this is an amazing experiment, and yeah, I really enjoyed this talk. Thank you very much.